Today, we are going to start by considering a very simple circuit. Just a lamp connected to a battery. The battery provides the energy that causes the free electrons to drift along the circuit in one particular direction, thus creating an electric current. On the other hand, the lamp consumes this electrical energy by converting it into heat and light. By the principle of conservation of energy, there has to be a perfect balance between the energy supplied by the battery and that consumed by the lamp, being the only device connected to the battery in this case. Now, suppose that the cell is rated 3 volts. In other words, it has an EMF, which is short for electromotive force, of 3 volts. The electromotive force of a cell is defined as the work done by the cell per unit charge that flows through it. By this definition, this means that 1 coulomb of charge gains 3 joules of electrical energy each time it flows through the cell. And don't forget that by 1 coulomb of charge we mean this amount of electrons, as we saw in our last session. The charge then loses this energy as it flows from the positive to the negative terminal of the battery, since it is used up by the components in the circuit. The positive terminal of the battery is said to be at a potential of plus 3 volts. This is another way of saying that at this point, 1 coulomb of charge has 3 joules of electrical potential energy. Assuming that no energy is lost in the connecting wires, in other words, assuming that the connecting wires have negligible resistance, we can conclude that any point along the circuit in between the positive terminal of the battery and the bulb is at a potential of plus 3 volts. Being the only component in the circuit, the bulb consumes all the energy by converting it into light and heat, and hence the potential at any point along the wire connecting the bulb to the negative terminal of the battery is 0. It can easily be seen that the left-hand side of the bulb is at a higher potential than its right-hand side. We say that a potential difference or voltage exists across the bulb. The potential difference or voltage across a component can be defined as the amount of electrical energy changed into other forms of energy by that component for every coulomb of charge that flows through it. Electric current always flows from a point of high potential to a point of low potential. If a charge Q flows through part of a circuit across which the PD is V, then the energy change W is given by W is equal to QV, where W represents the energy change in joules, Q is the flow of charge in coulombs, whereas V is the PD in volts. The units volts are thus equivalent to joules per coulomb. And in the case of uniform current I flowing for time t, then we can substitute using Q equals IT, and hence we get W is equal to VIT. Now, in the previous lecture, we mentioned that resistance is due to collisions occurring between the drifting free electrons and the vibrating positive ions. The resistance R of a conductor is defined as the ratio of the PdV across it to the current I flowing through it. So in other words, we say that R is equal to V on I. R is in ohms when V is in volts and I, the current, is in amps. And we can also define the conductance, symbol capital G, of a metal as the reciprocal of its resistance. So G is equal to 1 on R with units Siemens, capital S, equivalent to ohms to the minus 1. And here are a few symbols used for resistors in circuits. We have the fixed resistor, a variable resistor, and the potential divider, which shall be dealt soon, very soon. And these are a couple of short questions just to get you started on circuits. Now, let us analyze a circuit with two bulbs. The electrical energy supplied by the cell is consumed by both bulbs together. Let us suppose, for the sake of the argument, that for every coulomb of charge that flows through the circuit, the 3 joules of electrical energy provided by the cell, it has an EMF of 3 volts, so every coulomb of charge gains 3 joules. So let's suppose, for the sake of this example, that those 3 joules are divided or consumed as follows: 2 joules by bulb A and 1 joule by bulb B. This is shown as a PD across each bulb. So the PD across A is 2 volts and that across B is 1 volt. It is important for the student to note the difference between the values of the potential at particular points in the circuit and the potential difference across each component. So here we see that any point in between the positive terminal of the battery and bulb A is at a potential of plus 3 volts, since, as we said earlier, no electrical energy is consumed along this connecting wire. For the sake of the argument, we are taking the voltage across bulb A to be 2 volts, meaning that the potential at any point between bulbs A and B is plus 1 volt. So here we have the potential at a point is plus 3. Across bulb A, there is a potential difference or voltage drop of 2 volts, so 3 minus 2 leaves us with a potential of plus 1 volt at any point between bulbs A and B. The voltage across bulb B must then be 1 volt, which brings the potential at the negative terminal of the battery to 0. The PD across a particular component is determined by 2 rules, known as the potential divider rule of voltage division in a series circuit, which states, firstly, that the summation of all the potential differences across the individual components must add up to the EMF of the cell, So in other words, if we consider this general situation, we are saying that E must be equal to V1 plus V2. Secondly, in a series circuit, dPd across a particular component is proportional to the resistance of that component. So we are saying that V1 is proportional to R1 and V2 is proportional to R2. So this is what we said. E is equal to V1 plus V2. V1 is proportional to R1, V2 proportional to R2, and so even their summation, V1 plus V2, must be proportional to R1 plus R2. So if we divide 1 by 3, we get V1 on V1 plus V2, which is simply E, which is equal to R1 on R1 plus R2. And here we have the first result, where the voltage across resistor 1, V1, is found by dividing its resistance, R1, by the total resistance in the circuit, and then multiplied by the battery's EMF, E. So what we're saying here is that R1, resistor 1, takes a fraction of the battery's EMF across it. How much is that? How much is that fraction? It is this. Resistance R1 divided by the total resistance in the circuit. Similarly, dividing 2 by 3, we get V2 on E, which is equal to R2 on R1 plus R2. And we get a similar result to the first, where the voltage across resistor 2 is equal to R2 divided by the total resistance in the circuit, R1 plus R2, multiplied by the battery's EMF. These hold for any amount of resistances in series, such that if we say have 4 resistors in series, then dPd across R1 is simply given by its resistance R1 divided by the total resistance in the circuit, R1 plus R2 plus R3 plus R4, multiplied by the battery's EMF. So it's always the same pattern. And the advantage of using this method to calculate the voltage across resistors in series is that it doesn't require the current to be calculated if there's no need to. Here you have a simple question just to let you use the potential divider rule. Now, we can also devise a simple system using a light-dependent resistor or a thermistor to control voltage. An LDR, which is short for light-dependent resistor, here is its symbol, is a device whose resistance decreases as the intensity of light reaching it increases. It can be used, say, to control a night lamp, dimming the lamp or turning it off completely during daylight, whilst switching it on to full brightness at night. So during the day, its resistance R1 and hence the voltage across it, VAB, since these are proportional to each other, these will be at a minimum. But as the light intensity decreases during night, R1 and likewise VAB reach maximum values, this would then drive the lamp to maximum brightness. A similar voltage control can be designed using a thermistor. A thermistor is short for thermal resistor, here is its symbol, which is a device sensitive to temperature variations. So, replacing the LDR by a thermistor here, we get a simple but practical application such as a fire alarm. Now, let's move on to Ohm's law. Ohm's law states that under constant physical conditions, the resistance R is a constant independent of V or I and their directions. Under constant physical conditions basically means that the conductor is at a constant temperature and undergoes no strain. In other words, for ohmic devices, the PD across a component is proportional to the current flowing through it. Ohmic components are those devices that obey Ohm's law. So, for ohmic devices, mathematically, we are saying that the voltage V is proportional to the current I, with a constant of proportionality equal to the resistance R of the component. Now, an important note when using V is equal to IR. Attention must be paid to apply it properly if it is applied on a particular component in the circuit. Then all three quantities, V, I, and R, must belong to that particular component. Otherwise, V, I, and R could be total values, meaning that V is then the battery's EMF, I is the current through the battery, and R is the total resistance in the circuit. I will now let you try this question. Ohm's law is found to be obeyed by metals. The IV characteristics of an ohmic device, meaning the relationship between current and voltage, or in other words, a graph of I against V, is a straight line passing through the origin with gradient is equal to 1 on R. So from here, we can see that if we rearrange the equation V equals IR with the current as subject, then we get I equals 1 on R times V. So if we plot the current on the y-axis and the voltage on the x-axis, then we end up with a gradient equivalent to the reciprocal of the resistance. So this is the graph for ohmic devices such as metals. Now, such a graph can be obtained by conducting a very simple experiment using the circuit shown. So all we have here is a battery connected in series to the device under test, which in this case is a resistor. We are also including in the circuit a voltmeter to measure the voltage across the resistor and an ammeter to measure the current through it, and a variable resistor to allow us to vary the current in the circuit. In fact, we start by varying the variable resistor until we get the desired current through R, which is then read using the ammeter connected in series to it. And we also measure the PD across it using this voltmeter. The variable resistor is then adjusted at least 4 more times, each time taking the corresponding readings from the ammeter and the voltmeter for a total of at least 5 pairs of current voltage values. In the case of a resistor, the IV characteristics would be linear, as we've seen here, passing through the origin irrespective of the current direction. So both for a positive PD and a negative PD, we get linear characteristics, indicating that the resistor is an ohmic device, provided that we take some important precautions during the investigations. And these include primarily that the circuit is only switched on whilst taking readings to avoid excessive heat in the resistor, as well as the possibility of draining the battery. In addition, large currents through the resistor must be avoided in order to keep its temperature approximately constant. Other devices can be tested by replacing the resistor R, say by a filament lamp. We are going to investigate now the filament lamp, or discuss the filament lamp, the thermistor, and the diode. All of these components are said to be non-ohmic because they have non-linear IV characteristics. In fact, here we have the graph of current against voltage for the filament lamp, which shows that upon increasing the voltage, it becomes warmer and hence its resistance increases. Thus, the current increases but at a slower rate. In other words, the graph becomes less steep. A thermistor with a negative temperature coefficient, this is the symbol for the thermistor, is one whose resistance decreases as temperature increases. So the current through it is found to increase faster as the voltage across it is increased. So in other words, this graph is showing opposite behavior to the filament lamp in the sense that it becomes steeper as the voltage across the thermistor is increased. This is for a thermistor with a negative temperature coefficient, because there also exist thermistors with positive temperature coefficients, which behave exactly the opposite of the others. In fact, these are components whose resistance increases as the temperature increases. So in other words, we get a graph of current against voltage which is similar to the one for the filament lamp. Another non-ohmic device is the diode. This is its symbol. The typical IV graph for a semiconductor diode shows that this device only conducts when a PD is applied in one direction. We say that the diode is in forward bias, offering negligible resistance to current flow. This is shown by the sharp increase in the graph. It is very steep. On the other hand, the current nearly drops to zero when the PD is reversed and the diode is said to be in reverse bias. The diode will be treated in much more detail in a separate topic called semiconductors. It is important to note that for non-ohmic conductors, although the voltage and the current are not directly proportional to each other, however, the ratio V on I is still equivalent to the resistance R of the conductor at those particular values of voltage and current. In other words, it means that, for example, if we take again the filament lamp, its graph is shown here, we can go at any point along the graph, such as here, we note the corresponding current and voltage values, and the ratio V on I at this point will give us the resistance of the lamp at this instant.